we're going to talk about. So Newton's law of gravitation states that any two bodies with masses m1 and m2 a distance r apart attract each other with forces inversely proportional to r squared. These forces form an action-reaction pair and obey Newton's third law. When two or more bodies exert gravitational forces on a particular body, the total gravitational force on that individual body is the vector sum of the forces exerted by the other bodies. So the force of gravity equation equal to G m1 mass 1 mass 2 over r squared, where G is the universal gravitational constant, 6.67 times 10 to the negative 11, mass 1 in kilogram, mass 2 in kilogram, and R2. Careful, this is not radius. Not radius. Or it's not always radius. It's distance from center of M1 to center of mass 2. Center to center distance. And mass 1 is the mass of each object. And the units is Newton meter squared, kilogram squared. Let's do this. That's the value. Okay. And so on Earth, so the weight, the W of a body is the total gravitational force exerted on it by all other bodies in that universe. Near the surface of the Earth, mass is me and radius re. It is essentially equal to the gravitational force of the Earth alone. Okay, so weight equals Fg equals G mass of Earth for mass 1 and mass over R. So that's weight at Earth's surface. And the acceleration due to gravity on Earth would be GME RE squared. Acceleration due to gravity. But on other planets, it would not be using mass of Earth. So we know the equation weight equals mg. So on Earth, if it's Earth, then we can use g is negative 10. So that's why a lot of times we use a g of another, or if we're going to use this equation, we'd use another planet. Oh, I forgot to correct. Oops. So, for example, we could use this. Say you are 81 kilograms. Say your mass is 81 kilograms. On Earth, using weight equals mg, you do 81 kilograms times 9.8 and you'd get 794 newtons. You can also use this formula to use force of gravity, which is same thing as weight, equals G times mass of Earth times mass, and notice that's kilograms, 81 kilograms over r squared, which would be the radius of Earth in this case. And you should also get 794. Okay, so now let's talk about so this is the acceleration due to gravity for Earth. Now, any planet would be G, little g equals G m of planet over r squared. Acceleration due to gravity formula. G, little g equals big G mp over r squared. Okay, and now let's talk about how finding velocity of an orbit. Okay, so how do you find the v of orbit, the velocity of orbit? So we do Fc equals mv squared over r equals Fg equals m1, m2, or g m1, m2 over r squared. So it's not every case, but in this case, the radius is the same. So we can cancel that out. We can cancel out. So say this is mass of satellite and mass of Earth. Earth and mass of satellite. So we can cancel out mass of satellite. And then we get V equals square root G mass of Earth over R. Or the velocity of the orbit of the satellite. And to generalize it, we'll do square root G and P over R. So it's not always going to be like this. Like you can have maybe the R is not equal to that. It's like 2R or something. Or it's just you have to derive it every time by doing, right? Fc equals Fg. The mv squared over R equals, okay. That's how you find the velocity of an orbit. So now let's talk about UG. So when we do conservation energy, so UG equals negative GM1 M2 over R. So careful, we're going to do a comparison because it's an easy mistake that I made too. Versus Fg, force of gravity, equals Gm1 M2 of R. So the difference, they're pretty much the same, except this is R and this is R squared. So don't get those two mixed up. So So let's say we're looking for so that's conservation energy. Now let's find, how do you find escape speed? So escape speed is when the when the like satellite or rocket is infinitely far away, so that it's so far away that the force of gravity is zero, because it's so far away there's no attraction. It's too far away. So how we do that is we use conservation energy. U initial plus, or I missed the K. K initial plus U initial equals K final plus U final. This equals 0, so 1/2 mv squared and then plus, and not 1/2 mgh. We're using plus negative, using this gm1 and 2 r equals 0 plus 0. So this escape speed is this velocity when both are 0. So it's got this in the bottom marker. So then we do 1/2 mv squared equals gm over r. So we can cancel out the m. V equals 2gm1 r squared. So that's escape speed. And again, you have to derive this. You cannot just have it. And this versus v escape versus v orbit. Is this. So the only difference here is a 2 in escape. But again, it could be different because we need to derive these. And now for problems that are asking for the total mechanical energy. How you do those is just K plus UG. So 1/2 mv orbit squared plus negative gm m over r. And yeah. Now, whenever it mentions work, we use negative delta here. Right, like work equals delta kinetic energy, work equals negative delta UG. So last part we're going to talk about is when is angular momentum conserved. That is when angular momentum is conserved when torque is 0. So angular momentum is conserved in all satellite problems. So if we're finding, like, if they're asking to find R2, for example, then you can use RMV equals R2 and V2. The mass of this cancels out, and then we can find R2 equals R1 V1 over V2. And then Kepler's 3 laws. And this is conservation of angular momentum. And Kepler's 3 laws. First one is that it's a closed ellipse orbit. So it moves in an elliptical orbit. 2, L is conserved or same area. The third one is starting from FC equals FG. So like the T, the period, to R to 3/2. And another point that we actually haven't talked about that is very important is distance equals velocity over time. Or no, velocity, no, that's not true. Velocity equals distance over time equals 2 pi r over time, or over period. So velocity equals distance over time equals 2 pi r over period, big T. Okay, and that is the conclusion of the video.